Welcome to the lecture of mathematics. Today is the 26th of March 2026 and today we will look at the Laplace transform as already noted yesterday. So we start with some notation remarks. Basically the same as yesterday, but just so that you have it in the same document. R of t is denotes the general input signal. It can be for instance, the unit input signal, the step input signal, or some other. Y of t denotes the output. Signal, and u of t denotes the unit step function. Which is going to be interesting for us later on. So the Laplace transform is defined as follows. For the unit or for the function f of t, the so-called one-sided Laplace transform is defined by f, big F, okay, of S equal Laplace transform L of f small of t. And the definition is the integral between 0 and infinite of the function times the exponential negative st dt, whereas s belongs to the complex numbers. Okay, so this is the definition of the one-sided Laplace transform, which is the one we are looking at for our purposes. Okay, so this is the definition that most engineers use because it starts in 0, okay, and naturally incorporates initial conditions. So S, as we saw in the first lecture, can be described as sigma plus the complex unit times omega. So as a result, we can write A minus st equal A minus sigma plus j omega t, which is A minus sigma t times E minus j omega t. So this factor describes decay or growth depending on the symbol of sigma, and this factor contains oscillation. This we have already seen in the first lecture. Okay, so this is a definition, and So we take it from here. And now we apply the Laplace transform to many useful functions, okay? So the first one is the constant function. Laplace transform of the constant function. So if f of t equals a constant k. Okay. So the Laplace transform, let's compute it. Laplace transform of k equals the integral of between 0 and infinite of k times a minus st dt. So this is minus k divided by s e minus st between values of 0 and infinite. So this is k divided by s. Okay. This is an important result. So the second important result is the Laplace transform of the exponential function. So f of t equals e at. A belongs to the real numbers. So the Laplace transform of e at is equals the integral between 0 and infinite of e at times e minus st dt. And this equals 0 and infinite of e minus a minus s minus a t, and this equals 1 divided by s minus a. So you see here there is a change of a symbol. Here is with plus, and here it will appear as minus. If here it's with minus, then it will appear with a plus in the other side. Okay. Any questions so far with these two basic Laplace transforms? Yeah, we apply the definition of the Laplace transform is the integral between 0 and infinite. We can define it in a different way, but this is the more engineering way. The reason is it starts in 0, so it gives you naturally initial conditions, which for an engineer is the best. Okay. It's not a pure mathematics, but we are not in a pure mathematics course. We are in a course for engineers, so that's what we do. Okay. Yeah. So let's do an example. Imagine we have a function which is 3 times e minus 2 times t, okay? And we want to apply the Laplace transform to this function. Then the Laplace transform applied to this function is straightforward. Is the integral between 0 and infinite of 3 times a minus 2t times e minus st, yes, differential of t. The 3 goes out of the integral, is a constant. Then is the integral between 0 and infinite of e minus s plus 2 divided by t times t dt. So this is going to end up being 3 divided by s plus 2. Okay. Little example with the two transforms that we have seen. So what is the link to the complex numbers? So, and slowly all these lectures are joining together. We saw by Euler that E times JWT equals the cosinus of omega t plus J sinus of omega t. Okay. The Laplace transform of a j omega t, as we have seen from above, is 1 divided by s minus j omega. Okay. Second case above, we saw the exponential, so if we put here a is j omega, it's the same. Okay. So I guess this doesn't need to be real. It can be any number. So so which one is the Laplace transform of the cosinus of omega t? The Laplace transform of the cosinus is the Laplace transform of the exponential positive plus negative divided by 2. This is because the cosinus of omega t equals a j omega t plus a minus j omega t divided by 2. Well, this is simple. If we apply Euler here, the first one omega t plus j sinus omega t, and the second one is plus cosinus the minus omega t plus sinus j sinus of minus omega t divided by 2. Sinus of omega t is minus sinus, they cancel, and then and the cosinus of omega t is the same as the cosinus of minus omega t, so two cancels again, and then is checked. Okay, so the Laplace transform of cosinus is the Laplace transform of that. and that is equal to 1 divided by 2, 1 minus s minus j omega plus 1 divided by s plus j omega. This is going to deliver 1 divided by 2 s plus j omega plus s minus j omega divided by s squared plus omega squared. So this the Laplace transform of the cosinus function is s divided by s squared plus w squared. Okay, doing exactly the same for the cosinus, for the sinus function. You can do it if you want. It delivers omega divided by s squared plus w squared. So far we have 3 results. Let's summarize the 3 results. The Laplace transform of the constant function is k divided by s. The Laplace transform of the exponential function is 1 divided by s minus a. The Laplace transform of the cosinus function is s divided by s squared plus w squared, and the Laplace transform, let me put it in a pretty way. The Laplace transform of the cosinus function is s divided by s squared plus omega squared. The Laplace transform of the sinus function is omega of omega t is omega divided by s squared plus w squared. Okay, so these are the 3 results that we have so far. Any questions, please? So another useful result, number 4, is the Laplace transform of power functions. So the Laplace transform of the function t, if you do it, it will deliver 1 divided by s squared. In general, if you do t to the potent of n, it will be n period divided by s to the potent of s n plus 1. N period means n times n minus 1 times n minus 2 times so on, 3 times 2 times 1. Okay. So these are also important results, and we will see in an immediate application. Okay. So, any questions? examples. Compute the Laplace transform of 2 minus 5 e to the potent of minus 3 times t. Okay. This is the first one is straight. So we have a constant, so it's 2 divided by s. And the second one is another constant 5, and then minus 3t, then s plus 3. Okay, so that's the Laplace transform. Now compute the Laplace transform of 4 times sinus of 2 times t equals 4 times the sinus is omega divided by s square plus omega square. So 8 divided by s square plus 4. Okay. Any questions? These two examples. In this case, omega is 2. Okay, that's why 2 square. Questions, please. Okay, so the key properties of the Laplace transform. Are called linearity, and derivatives. Okay. So the linearity property is if we take two functions f and g and make a linear combination of them, then the Laplace transform is a linear combination of the two functions. This is called linearity. This is important for engineers because many models are usually linear combinations of signals. Okay. And then there is another property that is it's called the exponential shift. So if we multiply a function by a t, it's going to be a delay. The consequence is that we apply the function to not s but to s minus a. Okay, so this is called exponential shift. So the multiplication by a times 80 corresponds to a shift in the S domain. This is a very useful rule, okay? So these are the first two. This is just some linear. We can call this also a delay, okay? In engineering terms. The most important property, however, is the derivative, okay? And this is basically the reason why we use Laplace transform in the end. So if we say that the Laplace transform f on s is the integral, is written like this, okay? And then the Laplace transform of the first derivative is the integral between 0 and infinite of the first derivative, okay, times the exponential negative of st dt. We do this integral. We integrate by parts. So if we say u is e minus st and dv equals f first derivative dt, then differential of u is minus s e minus st dt, and v is f of t. Okay, this is instantaneous. So the integral of between 0 and infinite of the first derivative of f, a minus st dt, equals, because of the integration by parts, the function between 0 and infinite plus s, the integral between 0 and infinite of ft e minus st dt, okay? And this is basically minus the function in 0 plus s times the Laplace transform of the function f. As a result, this important derivative property of the Laplace transform arises. The Laplace transform of the derivative of a function equals s multiplied by the Laplace transform of the primitive function minus some initial condition. And this is the derivative property of the Laplace transform. I put also boxes in here to make it more clear. Okay. Of course, if we apply this rule again to this next derivative, then it turns out that it is s squared f of s minus s times in f0 minus f derivative initial conditions. Okay. So if we assume that the system is in equilibrium in the beginning, okay, so it's a zero. If we assume that f0 equals first derivative in 0, second derivative in 0, and so on. For instance, the system is in state of no motion in the beginning, then the Laplace transform of the first derivative turns out to be s multiplied by the Laplace transform of the function and the Laplace transform of the second derivative becomes s squared, and so on. Okay. So derivatives become algebraic powers. And the initial conditions appear automatically. So what we want as engineers is served. Okay. So this is a very good result. So any questions on this? Okay, let's solve an example. So this is a first order initial value problem. With Laplace. So imagine we have this differential equation, I first derivative plus 3 times I equal 6, and then the initial condition is 1. Okay. So we take the Laplace transform at both sides. Laplace transform of I plus 3 times Laplace transform of I equals Laplace transform of the constant. Okay. This yields S Laplace transform minus 1 because of the initial condition, plus 3 times E equal 6 divided by S. Okay, so the super complicated differential equation becomes piece of cake algebraic equation. So I of S, I big is multiplied by S by 3, S plus 3 equals 6 divided by S plus 1. Okay. So we turn this into I of s equals s plus 6 divided by s plus 3. Okay. This is the first step. Now we apply something called partial fraction decomposition. S plus 6 divided by s plus 3 equals one coefficient a divided by s plus second coefficient divided by s plus 3. We want to find out a and b. This equals a times s plus 3 plus b times s divided by s times s plus 3. So s plus 6 equal a times s plus 3 plus bs for all s. So if s is 0, then we have 0 plus 6 equals a 0 plus 3 plus b times 0. So a is going to be 2. And if s is minus 3, the reason why I do minus 3 or 0 is to eliminate, of course, these two and only get the other one. Is minus 3 plus 6 equals a times minus 3 plus 3, so 0, plus b times minus 3. So b turns out to be minus 1, right? As a result, we get that I of s, which was s divided by 6, s times s plus 3, yields a divided by s, also 2 divided by s, plus minus 1 divided by s plus 3. What I have done is put a and b here. Okay. So this means that implementing the Laplace transform in the other way, so the inverse Laplace transform of I of s, solving the equation, means inverse Laplace transform of 2 divided by s plus inverse Laplace transform of minus 1 divided by s plus 3. And this is going to yield 2 minus exponential of minus 3t. Okay. Which, if we represent the function, leads to this behavior. when this is I of t, this is t. When t is 0, the equation is 1, okay, because when t is 0, this becomes 1, so 2 minus 1 is 1. And when t is infinite, then the whole thing becomes zero. So it just turns out to be 2 okay. Okay. Any questions? So the initial value problem becomes an algebra problem, which is relatively easy to solve. So this is important, okay? Make sure you repeat this. There are many things that are relevant here, like the partial fraction decomposition. For you, let's do another example. I plus 2i equal 4, and the initial condition is 0. Okay. We apply again the Laplace transform, so s minus 0 plus 2 times is equals 4 divided by s. Is multiplying s plus 2 equal 4 divided by s. In the complex plane, is 4 divided by s times s plus 2. Okay. This yields, again, I'm doing this a little bit faster. 4 times equals a times s plus 2 plus bs. So if s is 0, then 4 equals 2 times a. So a is 2. If s is minus 2, 4 times equals minus 2b. So b is going to be minus 2. These results plugged in here, we get 2 divided by s minus 2 divided by s plus 2. Okay. Applying inverse Laplace transform, we get 2 minus 2 exponential of minus 2t. Okay. So this means the equation that we get is something like this. For t0 we get 0. When infinite we deliver something like 2. So it's going to be something like that. Okay. So this could have been solved easily with integrals and stuff, but when things get tough is when we have systems with more than first order. So let's say second order. Second order initial value problem. So second derivative plus 2 times first derivative plus 5 times I equals 0 equals the initial conditions could be this. Okay. So the second value problem is something like if we apply Laplace, so the Laplace transform of the second derivative, as we saw, is the square of I minus S, the initial condition, minus the initial condition of the derivative, plus 2 times S, the function, minus the initial condition, plus 5 times the function. So the first derivative initial condition is 0, so we get S squared I minus S plus 2 times Si minus 2 plus 5I equals 0. So what we get is that S squared plus 2S plus 5 times I minus S plus 2 equals 0. Okay. So what we get is that I of S is S plus 2 divided by S squared plus 2S plus 5. Okay. So we have S squared plus 2S plus 5. We break this down into with the roots minus 2, 4 minus 20 divided by 2 times S. This is minus 2 plus minus J times 4 divided by 2. So this is going to be minus 1 plus minus J times 2. So what we have is that this thing is S plus 2 divided by S minus 1 plus J times 2 on S minus minus 1 minus j times 2. Okay, the two roots of the polynomial. So if we say I of s equals a divided by s minus 1 plus j times 2 plus b divided by s s minus 1 minus j times 2, we get following behavior: s plus 2 equal a multiplying s minus 1 minus j times 2 plus b multiplying s minus 1 plus j times 2. Okay, so if s equals minus 1 minus j times 2, then we have minus 1 minus j times 2 plus 2 equal a times 0 plus b times minus 1 minus j times 2 minus 1 plus j times 2. Minus 1 goes with this away. So we have 1 minus j times 2 equal b times minus j times 4. Okay, so b is going to be 1 minus j times 2 divided by minus j times 4. If we multiply by complex conjugate up and down, then we get the final value of b, which is going to be j times 4 plus jj is minus 1 plus minus 1, 8 divided by 16. Okay, if we simplify, we get 2 plus j times divided by 4, and this is the value of b. If we take s equal minus 1 plus j times 2, then we get minus 1 plus j times 2 plus 2 equal a multiplying minus 1 plus j times 2 minus 1 minus j times 2 plus b times 0. Here again, minus 1 goes with this one. So it turns out that 1 plus j times 2 equals a multiplied by 4 times j. So as a result, a equals 1 plus j times 2 divided by j times 4 multiplied by complex conjugate up and down, we get that this is going to be minus j times 4 plus 8 divided by 16. So a is going to be 2 minus j divided by 4. Okay, we have a. So the result is going to be, if we put all together, ys equals 2 minus j divided by 4, 1 divided by s minus 1 plus j times 2 plus b is 2 times 2 plus j divided by 4 times 1 divided by s minus 1 minus j2. Okay. Applying the inverse Laplace transform, we would get the solution. So 2 minus j divided by 4, and then a minus 1 plus j2 times t plus 2 plus j divided by 4 e minus 1 minus j2 t. Okay. This is the solution complete. If we simplify with Euler's formula, 2 minus j divided by 4 cosinus a minus t, and then cosinus of j2t plus cosinus of 2t plus j sinus of 2t plus 2 plus j divided by 4 a minus t cosinus of minus 2t plus j sinus of minus 2t. In the end, what we get after simplification is that sorry, I got an email. What we get after simplification is that this whole thing is e minus t cosinus of 2t plus 1 divided by 2 e minus t sinus of 2t. Okay. So when we paint the solution, the whole thing ends up being when 0 it's just 1, okay, because the sinus of 0 is 0, so we start with situation in 1, which is the correct initial condition, okay. remember the initial condition was that this is 1 in the beginning. And then it's a negative exponential, and in the end, when t is very big, the whole thing goes to 0. But with some decay. Okay. And this decay is described by this two situations. So this is going to be very important in the next lectures to describe logistic processes. Just as an example, so that you have seen one, please fight it, okay? Fight it hard, it will pay off. So I'm going to write you a Laplace transform dictionary, okay? If we have 1 divided by s plus a, then applying the inverse Laplace will yield e minus at, and applying Laplace to e minus at will yield 1 divided by s plus a. Okay, so if we have 1 divided by s plus a squared, applying the inverse Laplace will yield t times e minus at. Applying the Laplace to e t times a minus at will yield 1 divided by s plus a squared. S plus a divided by s plus a squared plus w squared is EAT cosinus of WT, and the other way around is similar, okay? And W divided by S plus E square plus W square will yield and the other one in this way, okay? Okay, so any questions?